Welcome to part 2 of Kepler's first and second laws in basic planetary motion. In this video, we're going to put a little bit of the math and equations that we know from mechanics, from forces and energy, and incorporate that with Kepler's laws. So the first thing we want to remember here is that for an ellipse, the eccentricity of the ellipse falls somewhere between 0 and 1. Of course, the 0 is, if it has a 0 eccentricity, that's going to be considered a circle. And the higher the eccentricity goes, the more elliptical the path becomes. So just to give you a little bit of perspective, Venus has an eccentricity of 0.0068, which is very close to 0. Earth is pretty close there. I think it may be the third most, or third lowest of the planetary eccentricities, which is around 0.0167. Then on the other end of the spectrum, we have planets like Mercury, which of course is our closest planet, with an eccentricity of 0.2056. So quite a bit larger than these two. Pluto, of course, which whether you consider it a planet or not, it has a pretty high eccentricity of 0.2488. So as we look at these different planetary orbits, what we can see is that they're actually very close to being circular, and that actually turns out to be very helpful in making approximate calculations. And so what we can say here is that even though this looks very circular, it is technically an ellipse, with the sun here is at a focus, and these foci are so close together that it's actually hard to tell. But what we can do is we can take an average radius value or an average distance value, and we can actually use that to make some calculations. So what we're going to say here is that these orbits are going to be approximated as circular because the eccentricities are so low. And in that case, what I can say is that the gravitational force between the sun, which I'm going to label as m sub s here, and a planet, m sub p, are actually going to be held in place by the gravitational force. Now just recall that the gravitational force is equal between the two planets, meaning the planet is pulling on the sun just as hard as the sun is pulling on the planet, but because the mass of the planet is so much less, it's going to have much more of an acceleration than the mass of the sun. So if we expand our equations here, the centripetal force equation we know is mv squared over r, and the m in this equation is always dealing with the object that is doing the rotating. So that's going to be mass of the planet here. R, of course, is going to be the average distance between the sun and said planet. On this side, we're going to use Newton's law of gravitation, which is G times m over r squared. And of course, here we have the mass of the planet and the mass of the sun, the two masses that are interacting. And again, this is the average radius between the two. So it's clear now that we can make some simplifications. We can get rid of the mass of the planet, and we can actually simplify the square out of this equation as well. And this leaves us with V being equal to G times the mass of the sun over R average to the 1/2 power, or the square root of G mass of the sun over R average. Now what this shows us is what's known as the orbital speed. And the orbital speed, this of course is going to be an average orbital speed because we have an average radius here, shows the relationship that we would expect from Kepler's second law, which is that when the average radius is lower, the velocity is higher. So there is this inverse relationship between the two. In other words, when I'm closer to the sun, so when my R average is lower, or my R is lower, I should have a higher velocity. And that does agree with what we discussed from Kepler's laws. You can also think of it from the perspective that the gravitational force is inversely proportional to the distance between the two masses squared. So that means when the distance is quite small, or small compared to other times in the orbit, the gravitational force is stronger. And we can see here that when we approximate the gravitational force as being a centripetal force, that there is a direct relationship between the gravitational force and the centripetal force. This means that Obviously, when the radius is smaller, force of gravity is higher. When the gravitational force is higher, the centripetal force is higher. And finally, we can take a look and say that the centripetal force is proportional to the velocity squared. So when the centripetal force is larger, the velocity will be larger as well, which supports Kepler's second law, which is great. Now let's take a look at this from an energy perspective, which takes a little bit more math and analysis. Let's start with an analysis of the gravitational potential energy of this interaction. Now we know that the gravitational potential energy is equal to the negative integral of the force dot the path or radius. Now this is a dot product, and that's actually very important here. What we're going to assume is that the radial vector, or the position vector, is pointing outwards like this, okay? Which means that the force vector is pointing inwards because that's where the gravitational force is pulling this planet. And so this F dot dr actually turns out to be negative as well. Now what that happens to do is make this whole thing positive, so what we end up with is integral F dr. Now the F here, the force that's actually contributing to this gravitational potential energy, is G times m sun m planet over r squared. And so that's what we're going to factor in here, or what we're going to substitute in here. So we're going to go ahead and we'll put this in. We have G times m sun times m planet over r squared times dr. We're going to then integrate this from infinity, we'll talk about y in a second, all the way to the position of where the planet's actually located. So the reason we do this is actually just to make an easier way to compare different gravitational potentials, because we know that all the way out at infinity, the gravitational potential energy is just going to be 0. And at the position r relative to where the object's located from the sun, there will be X amount of gravitational potential energy that we can have. So let's go ahead and do this integration here. So we're going to pull all these constants out, G, m sun, m planet, and we're going to integrate then just 1 over r squared dr, or dr over r squared. And if we remember our integral identities, what we're going to end up with here is that this is equal to negative 1 over r. So this would be negative G ms mp over r, and that's going to be our equation for gravitational potential energy. And so we can see that this is actually a negative value. So if you were going to make a little graph here between radius and gravitational potential energy, what you would see is something that looks like that. Now, one thing I think is really cool about this graph is that there's a point, maybe let's call it right over here, where we're actually at the radius of the planet, so the surface of the planet. And so all this energy over here actually is not accessible, because when we are dealing with this R value, we're actually measuring from the center of the sun to the center of the planet. And so what we see here is that in order to get enough potential energy, or enough energy in general, to pull this planet away from its whatever it's orbiting, so in this case the sun, it would actually take quite a lot of energy here in order to do that. And so you can think about how this graph could help you in solving various problems. The main thing to remember here is that for the gravitational potential energy of something in orbit, we always want to include this negative sign here. If you don't, you'll end up with some pretty terrible mistakes in your calculations. Now we could say that the total energy of the orbit would be equal to the kinetic energy minus that gravitational potential energy. If you put plus here, we know that obviously the minus is represented over here. And so you can see that when the gravitational potential energy term is lower, the kinetic energy term could be changed as well in relation to the radius away. So hopefully that helps. In the next video, we'll take a look at the Kepler's third law.